Hi, I'm Kinry Watson, and today we're going to be putting trigonometry back together. So if you're trying to make a facsimile of a curvy thing because you want to do math to it, the way that you start is not by trying to do math to the whole curve all at once. It's easier to choose points and do math to them individually. And so to start this part of our journey, we're going to use a tool that mathematicians have come up with called the unit circle, which is the most basic circle imaginable. It's got a center at 0, 0 on the xy axis, and it has a radius of 1. And so what we're going to do is take the special right triangles that we've talked about from our SOHCAHTOA video, and we're going to begin placing them on the unit circle to ascertain different points on it. Let's get started. So some other things that we know about the unit circle right off the bat is these 4 points where it intersects with the x and y axes. So here, if the radius of the unit circle is 1, the point is at 1, 0, because we've gone out 1 unit and up 0 units. And up here, where it intersects with the y-axis, we're at 0, 1. Here, where we touch the x-axis again, we're at negative 1, 0. And here, where we touch the y-axis again, we're at 0, negative 1. Let's try to approximate some of these points. The right triangle, whose 2 sides are the same. Because that means when the radius is 1 and the 2 sides are the same, it's going to be pretty easy to figure it out using just the Pythagorean theorem. The angle that gives us this triangle is 45 degrees. And so we end up with two 45-degree angles and a right triangle, and a right angle, and 2 x values that are the same. So when you apply the Pythagorean theorem to this triangle to solve for these sides and what length they are, remembering that the Pythagorean theorem is a squared plus b squared equals c squared, we can say x squared plus x squared equals 1 squared, which is pretty easy to simplify to say 2x squared equals 1. And so to begin solving for x, we divide by 2 and take the square root of both sides to get rid of the exponent. And so you end up with x equals square root of 1/2, or 1 over the square root of 2. And while that's a satisfying answer to some, what you'll see on your unit circle is that this answer has been rationalized or multiplied by root 2 over root 2 to get rid of the radical. And so what you end up with for most trigonometry classes is root 2 over 2 as your answer for x. And so when we put this triangle on the unit circle, what we'll see is for the angle 45 degrees, we've gone over root 2 over 2 and up root 2 over 2, which allows us to approximate this point. And to help us put it on our big unit circle, I've made this handy dandy angulotron. Now that we've solved for the sides of our special right triangles, we can start putting them on the unit circle to find the points. Let's start with the first one that we did. So this is our special right triangle with a 45-degree angle. And so we know that a 45-degree angle where the hypotenuse is 1, this side is root 2 over 2, and this side is also root 2 over 2. Which means this point, where the triangle intersects with the unit circle, is at root 2 over 2, root 2 over 2. We also know that we can flip this triangle around to find similar points in other quadrants. So in this quadrant, we take the same triangle and the same ratios, and we put it in this other quadrant, which means that this point is also root 2 over 2, root 2 over 2. Except, since it's on the graph, and we're on the negative side of the x-axis, the x point has to be negative. When we flip into the third quadrant, both points have to be negative. And so this is negative root 2 over 2, negative root 2 over 2. In this quadrant, the y point is negative and the x point is positive, which makes it root 2 over 2, negative root 2 over 2. We can get two more angles onto the unit circle with special right triangles though. And I think the easiest way to do this is by thinking about an equilateral triangle. So an equilateral triangle has all three sides the same and all three angles of 60 degrees. Which doesn't really help us just as is because we're trying to use the Pythagorean theorem, and so we need a right triangle. So the way that I like to think about it is if you drop an altitude from this top angle, you can make a right triangle with an unknown side, a right angle, a 30-degree angle, and a 60-degree angle. Zooming in on our right triangle, what we get is, since this is the radius of the unit circle, it's 1. And since this used to be an equilateral triangle, all of these sides are 1 as well. And so this side, which is halfway, because it bisects this top angle, is 1/2. And so all we need to solve for is this side, the side between the 30-degree angle and the right angle. So we're going to call that x. You know that this is 30 degrees, and you know that this is 60 degrees. So now what we have is two side lengths, and so we can do the Pythagorean theorem. Remembering that the Pythagorean theorem is a squared plus b squared equals c squared, we can write this as 1/2 squared plus x squared equals 1 squared, which is to say 1/4 plus x squared equals 1. And so to begin solving for x, we subtract 1/4, and that gets us x squared equals 3/4. And so if we take the square root of both of those, what you get is x equals root 3 over root 4, which simplifies to root 3 over 2, because the square root of 4 is 2. And so this side is no longer unknown. We know that it's root 3 over 2. And so when we go to put this triangle on the unit circle, we can do it two ways. We can put it as a 30-degree angle and know that at 30 degrees, you've gone over 3 root 2 and up 1/2. Or you can put it as a 60-degree angle on this side and know that you've gone over 1/2 and up 3 root 2. So that allows us to put 2 points on the unit circle in each quadrant. Here's our other special right triangle with the 30 and 60-degree angles. So if we start with a 30-degree angle and we place it in the first quadrant, we can see here at this point, well, let me do my other color. We can see here at this point we've gone root 3 over 2 units over and 1/2 a unit up, which means that we're at root 3 over 2, 1/2. We can also see when we flip it over into the fourth quadrant, we have a point that's root 3 over 2, 1/2, except the 1/2 is negative because we're on the other side of the y-axis. Continuing to flip this triangle around, we can also see that a 30-degree angle in this quadrant gives us the point negative root 3 over 2, 1/2. In the third quadrant, it gives us the point negative root 3 over 2, negative 1/2. The other thing that we can do with this special right triangle is hold it the other way because it also has a 60-degree angle. And when you put the 60-degree angle in the first quadrant, you end up with a point where you have gone half a unit over and root 3 over 2 units up. So you get your 1/2 root 3 over 2 here. 60 degrees on this side is the same with 1/2 root 3 over 2, except we're negative. 60 degrees in the third quadrant looks like that, and gets you the point -1/2 negative root 3 over 2. And 60 degrees in the final quadrant yields 1/2 negative root 3 over 2. And so those are the points that you will probably be asked to memorize if you're in a geometry class or studying trigonometry on the unit circle. Just with these two special right triangles, you can approximate the curvature of a circle without having to know any fancy equations. If you remember, all we had to do was use the Pythagorean theorem and what we knew about angles. So now that we've put all of our points on the unit circle, we can see that we have heights associated with various angle measures. But there's another way to talk about angles other than degrees. For example, we know that root 3 over 2, 1/2 is the coordinate point for an angle of 30 degrees. But most of the time, when you're doing trigonometry, you're not talking about degrees, you're actually talking about radians. And so, given all of these points that we know, we should be able to figure out what the radian measures for each of these points is as well, not just the angle measures. The first thing that you need to know when putting radian measures in is that, radians are related to the ratio between every circle's diameter to its circumference. And so since what we're doing here on the circle, finding these points, is related both to the circumference and the diameter of the circle, it's important that we use radians. That ratio of the diameter to the circumference is pi, 3.14. If you take the diameter of a circle and lay it around the circle's circumference, to get from your starting point to your ending point, you would have to lay down 3.14 diameters. Except a circle isn't really defined by its diameter, it's defined by its radius. And so when we talk about the circumference of the circle using radians, we say 2 pi, because the radius is half of the diameter. So if you took the radius and laid it on the circumference, you would have to go around, you would need 2 pi radii, to get all the way around the circle. And so one full rotation is 2 pi. And from there, we can begin to place our other points. Halfway around the circle is pi. A quarter of a way around the circle is pi over 2, which is simple enough, right? 2 pi, which is the same as pi over 2, 3 pi over 2, 4 pi over 2. Pi over 2, pi, and then 3 pi over 2. Those are our quadrantal points, which is all well and good if we know that 2 pi is the center. And now here, we run into some difficulties. The 30-degree angle, we know is 1/3 of 90, which is half, right? And so 1/3 times pi halves is pi sixth, and that's what we know that this point is. It's pi sixth. Our next point is half the way to 90, or pi over 2. So pi over 2 times 1/2 is pi fourths. And this final point (60 degrees) is 2/3 of the way to pi halves. And so when you multiply those together, you get pi thirds, which is the radian measure for 60 degrees. And you can do that going all the way around the circle if you wanted to. But instead, I'm going to show you a shortcut for doing it. So because you can remember when we put the 30-degree reference triangle on the unit circle to get our points, we flip them over. And so they're very similar coordinates except for the positive and negative. You can do that with radian measures too. You just have to add to where it cannot be reduced. So 1 pi sixth, 2 pi sixths is the same as pi third. 3 pi sixths is pi over 2. 4 pi sixths would be this point. And so 5 pi sixths is what you get here. 6 pi sixths is the same as pi. 7 pi sixths cannot be reduced, and so it becomes this point, just like when we rotate it down. 8 pi sixths comes this point. 9 pi sixths is the same as 3 pi over 2. And so when we get back here, 10 pi sixths can also be reduced. And so our final point of pi sixth, with 6th as a denominator, is 11 pi sixths, which checks out because 12 pi sixths reduces to 2 pi. This trick also works for pi fourths. So 1 pi fourths is pi fourths, 2 pi fourths is pi halves, 3 pi fourths cannot be reduced, and so we know it goes in this quadrant. 4 pi fourths is the same as pi. 5 pi fourths doesn't reduce. 6 pi fourths is the same as 3 pi halves. And 7 pi fourths is where we find ourselves before we get to 8 pi fourths, which is 2 pi. I really hope that's helpful. Next time we're going to move on to pulling some functions using our triangle ratios and graphing them. And after that, we'll get on to more fun stuff as we continue trying to put trigonometry back together. See you then!